So yeah, today I'm going to be giving a talk on, this is more of a Monte Carlo talk on non-reversible parallel temporal and optimized paths. I do not expect anyone to know what any of these words mean. So the motivating problem is that we want to compute expectations. We want to compute integrals with respect to general functions, with respect to general probability distributions, like over general state spaces. And in practice, like this is not going to be a tractable thing, but we want to still like get a number at the end of the day. So one of the most popular techniques that we can use is MCMC. MCMC involves running a Markov chain with the stationary distribution that is targeting the distribution of interest. And then you let it run for a long time, and then you average out, pretending that it is a probability distributions. And the ergodic theorem will tell you that if you average out the trajectory and look at the function on it, you will eventually get the expectation. That's a nice story that we tell ourselves, but in practice, that doesn't work very well. In particular, like multimodal distributions turn out to be a pretty big problem. So for example, like if I have a local region of high probability over here and a local region of high probability over there, then the valley of low probability in the middle, in theory, like I will make the traversal an infinite amount of time, but in the finite budgets that we work with, you're most likely going to get trapped in one mode and never see the other, right? And this could be problematic because it can trick you into thinking that you have converged, but in reality, you've actually missed a big chunk of your space because a priori you don't know where the modes are. And this problem gets even more complicated as soon as like as you increase the dimension of your space or dealing with more discrete topologies or constraints, they can get messy really quickly. So we want to build robust methods that can accommodate for that. So before going into like the solution, let's figure out like what's the problem, right? So why does this actually happen? And I'm going to make the argument that it's an inherent issue with serialness and MCMC. So there's a serial MCMC. So MCMC is inherently a sequential algorithm, right? You are constructing the next iteration based off of where you currently are. That's how Markov chains work. So what that means is that to get better performance, like you need to let it run a very long time. And hardware speeds have kind of the clock speeds have somewhat stagnated over the last like decade. So we're not really going to expect to see like large computational gains to be made by running things faster. Our computers are not much faster than they were before. Also, the task, like we're kind of requiring our MCMC chain to do two things simultaneously. We're requiring it to both explore very well, like look at all the different parts of the state space, but also exploit the places that are higher probability. These are in some sense orthogonal tasks, and in practice, it fills it both. So the solution is leveraging the fact that we live in a world where parallel computing is becoming far cheaper. And we want to be able to leverage that to increase the robustness of our MCMC algorithms. So I'm going to delegate the task of exploration to a reference chain. So something that maybe I can get IID draws from, something that we can tractably, reliably like explore. And we're going to use our other parallel processes to target different distributions that interpolate to the target. So inherently creating essentially like a bridge between the two. So you can use a reference for the exploration and use these interpolating distributions to communicate to the target, which is doing the exploiting. So this platform that I've been basically describing is called annealing. Annealing, for notational purposes, I'm going to say that pi1 is going to be our target. Think of the posterior in a Bayesian context, something that you can evaluate up to normalizing constant. Our pi naught will be our reference. This is going to be something that we can tractably, reliably sample from. Like think maybe like a Gaussian or like a prior or something, again, simple and tractable. And we're going to use pi beta to denote the annealing distributions, where beta is a continuous parameter that interpolates between the reference and the target. So the most common way that this is done is through what I'm going to call the linear path, which is linearly interpolating between the reference and target in the log space. So in the y-axis here, you can see the beta, right? So in practice, like we don't live in a world of where we can do continuous things. We have to use, for actually like having algorithms, you have to discretize. So we're going to like partition our like interval 0, 1 into beta naught to beta n. where n is the number of interpolating points. And we're going to call this the annealing schedule, and beta the annealing parameter. So notice how as I increase beta from 0 to 1, I'm going to slowly deform my unimodal reference into a maybe multimodal target. So you can already kind of see just from this picture why annealing has the potential to like be quite useful for dealing with multimodality. We're effectively turning this multimodal problem in whatever dimension you're working in into a unimodal problem in one dimension higher. So by effectively using this reference distribution as a centralizing point to create a tunnel between the different modes. So annealing itself is not an algorithm, but it's a platform to build algorithms on top of. And so the one that I want to be talking about today is called parallel tempering. So parallel tempering, what it's going to be doing is we're going to construct a bigger Markov chain. We're going to make the problem a bit more complicated. So instead of just sampling from the target distribution, we're going to construct a vector that's targeting all n of them simultaneously. So the last component will correspond to the reference, the first component will correspond to the target. And so we're going to construct this Markov chain with this right station distribution, and then we can recover our expectation that we cared about initially just by marginaling out and just like chopping off all the other components, just looking at the last one. So assuming we can construct this, then we now have a recipe. So now let's talk about how we can actually construct it to do the thing that we want it to do. So I'm going to describe how we construct the MCMC, the parallel tempering chain. Like each iteration will correspond to 2 steps. So I'm just going to be showing you 2 components here, but there are n of them. The first thing that we're going to do is we're going to apply a local exploration. So this is, we already have assumed that an MCMC algorithm for each of our components. So what we're going to do is just apply that MCMC algorithm independently to each component. So notice how the state that was closer to the target, the peakier one, it was able to, it got stuck in the mode, whereas the one that's a bit flatter has the capacity to maybe traverse the mode a little bit because it's a bit flatter. So up until this point, the local exploration move isn't really doing anything. We've just essentially added more complexity without letting any interaction happen. So the parallel tempering part of parallel tempering is in this communication step. So the communication step, what it allows you to do is allows for adjacent states to basically interact with each other by proposing a swap. So what we're going to do is the state that is at beta n, we're going to propose that to beta n plus 1, and the one that's at beta n plus 1, we're going to propose that down to beta n. And we can't always accept. We're going to have to reject some time to preserve this right station distribution. But if I reject, well, in that case, nothing has happened. I've just stayed where I am. I've effectively just done the local exploration move, which I haven't lost any computational effort. However, if I accept, there's the potential for movement to occur that's quite dramatic. So notice how if I accepted, I started off initially at that state in the left mode, and I ended up at the right mode in one iteration. And that interaction happened through the reference, not the target itself. So if you do this correctly, with a sufficient number of chains and you allow for things to be optimized correctly, this is the type of results you can get with parallel tempering. So this is the exact same problem, but then we applied parallel tempering as a meta algorithm. And notice how it not only just traverses the modes and discovers them, but it does so reliably and often. And this is, so just to show that it's not just a toy Gaussian thing, we've actually, these are examples of challenging multimodal problems that come up in practice with real data. And you can see that with a single chain, you often get trapped, whereas with parallel tempering, you can actually get some pretty remarkable results. So up until this point, I've described parallel tempering, but there's a lot of, I've brushed a lot of details under the rug. How do you actually tune it? There's a lot of moving parts, and if you kind of mess up any one of them, it turns out to be quite fragile. So how do you propose the swaps? Well, the way that people typically do it is by you close your eyes at random, you pick 2 chains, and you propose a swap. And what I'm going to call that is a reversible move. What that basically means to preserve detail balance and the right station distribution, which is an easy thing to do. What this reversible moves allow you to do is like, well, you are communicating effectively through a random walk, right? When I'm moving states towards the target one iteration, the next iteration I can also go backwards. And that's going to create this like random walky type behavior, which doesn't scale very well. So what the design recommendations prior to our work was with this reversible methods was you want to reject 77% of your swaps to maintain a certain amount, to ameliorate the inefficiencies that come from a diffusion. How do you pick the schedule? Well, like that was also a really challenging problem. You actually got worse performance by adding too many chains because random walks scale, the amount of time that it takes to make the traversal with a random walk grows quadratically. So that required you to do these like complicated stochastic optimization techniques, which in my opinion are even more challenging than parallel tempering itself. Because you had this deterioration in performance by adding too many chains, the design recommendation was to pick n as small as possible and try to even reduce over time. So if I have access to a GPU or like hundreds of like parallel processes at my disposal, I can't really use them with the previous methods. How do you actually pick this path? Like there is nothing special about the linear path, but that's what people typically pick. And more importantly, like how do I know if it's actually like a hard problem or a bad implementation? Right? Some problems are hard and you should expect to pay a penalty for that in terms of computational effort, but sometimes it's your fault and you want to be able to identify when that's the case. So before talking about how to resolve these issues and like what is like it means to have a good parallel, first we want to ask like what does it mean to have a good parallel tempering algorithm? And again, I want to really focus on the fact that communication is the thing that we care about. We want like as much information from the reference to percolate its way to the target. So what I'm going to call a restart is when a state travels from the reference to the target. So whenever that occurs, we're going to say a restart has occurred. And the thing we want to maximize is the total percentage of restarts that have occurred throughout the MCMC run. So what I'm going to call the restart rate. So it's a percentage of that restart. So the solution turned out to be in the computational chemistry literature, and it was hidden away, and it was called what I'm going to be calling the deterministic even-odd swap. It's a two-line algorithmic change, but what it requires you to do, instead of like closing your eyes and picking two like states at random and proposing swaps, what we're going to do is deterministically alternate between even swaps and odd swaps. So odd, even, odd, even. So odd swaps, I mean, proposing swaps between chains n and n plus one, where n is odd. And even swaps are going to be proposing chains, swaps with chains n and n plus one, where n is even. So you go even, odd, even, et cetera, et cetera. So notice that this preserves the right station distributions. But more importantly, if I propose a state towards, like, let's look at this bold line. If I go towards if I'm going in one direction in one iteration and I accepted, the next iteration I'm going to also be going in the same direction, and I'm going to keep going in the same direction until I hit a rejection, and then I reverse. So I'm basically imputing in a momentum into the trajectories, and the fact that I'm alternating between these odd and even swaps, what that basically means that when one iteration to the next, I'm never going to propose the same swap twice. So that means that I never have the capacity to reverse direction in one move. What this basically means is like, so what we were able to show essentially is that this, in terms of restart rates, non-reversible parallel tempering with this, again, two-line algorithmic change dominates the restart rate of reversible parallel tempering. But more importantly, like you can actually do like the analysis, like what happens if I, let's say, the number of chains or the number of parallel processes get really large. So with reversible parallel tempering, it actually becomes quite fragile because remember, it takes O(n) squared iterations for a random walk to make a traversal, whereas it takes when you're only increasing the number of chains by O(n), so the diffusion wins. So you actually, by adding too many chains, the diffusion starts to occur, and you can show that the scaling law turns out to be a Brownian motion on the interval 0, 1, and it actually it becomes quite fragile, and you're not going to have any. The restart rate is actually going to go to 0 by adding too many chains. Non-reversible parallel tempering, in contrast, is actually gets better by adding more parallelism. So by increasing the number of chains, you get better performance, up to marginal gains by this number, what I'm going to call lambda, or the communication barrier. So there is a no free lunch. You're never going to get, there's a certain limit that you can achieve. But the fact that it doesn't go to zero and you actually get better performance by adding more chains is, it's a quite dramatic change. And the scaling laws here, as you can kind of see, like they stabilize to a piecewise deterministic Markov process. The details aren't relevant, but the main thing is that it is fundamentally different than diffusion. And the scaling law, the amount of, the scaling time is actually ON rather than ON squared. So this process, what essentially is doing is that you're going to be going in a straight line until you hit a rejection, which occurs at rate lambda. And then you're going to keep going in the same direction until you hit a boundary or a reject again, and so on and so forth. So how do we actually like use this? So like this previous slide is more to justify that the non-reversible parallel tempering is fundamentally different than the previous paradigm of parallel tempering. But now we want to actually like leverage this and to, tune PT and to understand how to do it properly. So when I'm going to define the rejection rate, I'm going to view it as a divergence. So the rejection, so if I look at two distributions and look at the swap rate between the two, the rejection rate is going to be determined by like the overlap essentially between the two adjacent distributions. So if the two distributions adjacent have a lot of overlap, then the rejection rate is going to be close to zero. And if there's very little overlap, it's going to be close to one. It's very analogous to a total variation distance. So we can use by looking at essentially the derivative of this like rejection rate, if I make a small perturbation along the path, I'm going to get what I'm going to call like the local communication barrier or the speed of the path. This effectively measures like how rapidly your path is changing for a small change in beta. And then the length is going to be the integral of the speed along the path. So the lambda quantity for the communication barrier is effectively quantifying the cumulative like change that occurs along the path as measured by the rejection rate. So the rejection rate is something that you keep track of anyway while running parallel tempering, but it turns out to be a third order approximation to the integral of this local communication barrier. So what that means is by summing up all these rejection rates, I actually get a really good second order approximation to this lambda. So it's not just this theoretical abstract quantity, it's something we can actually like quantify and measure. So the optimal schedule is the one that maintains the rejection rate as constant. So i.e. the integral between the speed curve is constant. So for something like, where weird phase transitions or complicated things that can occur along the annealing path, what this is saying is that you want to put more annealing distributions in places where rapid changes are occurring. For example, in the easing model where you have like a critical phenomenon, you want to put more distributions, whereas when things are more stable, you can get away with spacing out your distribution annealing parameters a bit more. So you can also use this to specify what is an optimal path. So we can interpret this like lambda quantity as a length. So we can start asking like, okay, given a family of paths that I have to play around with, or like a space of distributions that I'm working out with, like what is the shortest distance path? So you can effectively quantify the notion of tuning parallel tempering and the path via geometry and some geodesics. So the optimal path is one that's trying to simultaneously move the mass from the reference to the target while maximizing the overlap along the way. You can show, for example, this linear path, like for two Gaussians with different means and same standard deviation, as the means get further apart, the linear path, the length will grow linearly. Whereas with the optimized path, like the length will grow logarithmically. That basically means that you can get an exponential gain in performance by picking a better path if you do it correctly. So how do you actually like do
this? Sorry, you have 3 minutes more.
So basically, like you can use the fact that you can sum up these rejection rates to construct a very simple iterative algorithm, which I'll remove the details of, but it is a very cheap and easy thing to do. So we benchmarked this against 16 different problems, essentially of various complexities, data sizes, including like a 192,000 dimensional phylogenetic inference problem. And we see that in all of our scenarios that it actually stabilizes and converges. just to show you what the weird complexities that can occur in that time. We found that an ESS improvement of 10 to 100x compared to the previous state-of-the-art methods. And our work has also been applied to various domains independently of our team, including cancer, nuclear fusion, probabilistic programming that has led to us work in some top-tier journals. And most notably, the Event Horizon Telescope in 2019, they used parallel tempering to actually generate the photo of M87. And so this was done before our work, but in 2020, they implemented our implementation and they were able to recreate the results of the photograph from 5 days to 45 minutes, but also more reliably. So this was the computational advancement that was required to discover magnetic polarization in M87 with these swirls, as well as the photo of Sagittarius A star last year. These were only possible because of our algorithm. So in summary, non-reversible parallel tempering is better than reversible parallel tempering. If you tried PT in the past, it's worth trying again. We've identified scaling limits with increased parallelism. We have characterized the optimality in terms of tuning and schedule, as well as developed actual natural efficiency metrics. Our analysis also makes no structural assumptions on the target or state space. We truly view it as a meta algorithm. We also have an efficient black box algorithm for tuning PT that scales to modern computational architectures. If you want to try out parallel tempering, you should check out our package pigeons.jl or read our papers. Thank you.
Thank you. Is there any question?
Yeah.
I will have just one. Is it non-reversible type computationally more complicated than reversible?
No. So the reason why reversible methods are typically used in in computational statistics is because they are easy to design, but they're not necessarily better. So in particular, in this case, the only algorithmic change, if you already say have an implementation of reversible PT, is instead of proposing swaps at random, you are now deterministically alternating between the odd and even swaps. The cost of the swaps is exactly the same. So the only thing that you're changing is the order, and that is, computationally identical.
Okay, thank you. Andre?
Thank you for a nice talk, Saifuddin. So my question relates to comparison to other Bayesian computational methods. You compared, I think, non-reversible to reversible tempering, but how would this compare, say, to other, even MCMC approaches, like Langevin and so on, or others?
Yeah, so in our paper, we have far more. So my paper and thesis, we've benchmarked against a lot of other stuff as well. So again, so parallel tempering is not a competitor to MCMC algorithms. It is an addition, right? So if you already have an MCMC algorithm, you can use PT to make it a better one. Essentially, the input is an MCMC. So it is not a competitor to something like Langevin, but it would be, say, a competitor to other annealing methods such as annealed importance sampling or sequential Monte Carlo. So our work, we now find, is competitive with the state-of-the-art in SMC and AIS. So in some sense, right now, I'm actually writing a paper, which hopefully in the next month it will be out, that actually doing the unification and benchmarking against the two. So in some sense, you can think of the SMC and parallel tempering as computationally dual frameworks. So SMC is inherently built around importance sampling, which is inherently a distributed algorithm, right? So you can use annealing to add a sequential term, a sequential cost to add more robustness. Whereas with parallel tempering, if you remove all the annealing, it's essentially independent metropolis hastings with MCMC. So MCMC is inherently sequential. So the annealing here is used to add parallel cost to add robustness. So depending on the computational limitations or your computational budget, as well as the hardware considerations, that should be the thing that distinguishes when you should use one versus the other. But if you are rich in time, rich in parallel resources, the punchline is turns out they're basically the same.
Okay.